Welcome to Rep tutorial. This tutorial is a tutorial which presents step-by-step procedure to model unsteady river flow by using HEC RAS. HEC RAS is a software developed by US Army Corps of Hydrologic Engineering Center. Here I am using the latest version of HEC RAS, and if you want to download it, you can get the link in description. For modeling unsteady river flow, I will use the following problem. This problem, which includes also this table. Important basic data are given, which HEC-RAS uses to model unsteady flow. Let us begin by creating new project in HEC-RAS. Open HEC-RAS. Create new project. Here, before naming the project and the file, it is better to browse the folder where we want to save it. So I want to save let's say project title unsteady flow project. Here the project title, the file name. Say OK. Again OK. US customary is to be used, but we need to change that one into SI unit system. So select option, then unit system, then system international. Select, then OK. Say yes. The next step is to enter geometric data by selecting edit, then geometric data. Here the problem has no background river map, so I am using directly to draw river ridge. By selecting river ridge. Here this mark informs me river ridge is selected. Then begin by clicking at some point here and extend your line at some point here, and at the end double click. HEC-RAS asks to name river and ridge name. So say river Y and ridge X, then OK. The next step is to enter cross section So select cross section and enter cross sectional data by selecting option, then add new cross section. Here the river station which I will enter is the downstream most station. So HecRAS considers the lower number as the lower and the higher number as the upper or upstream station. So this 00 is the lowermost station, and no station is represented after that. So say OK. Here river Y, reach X, station 00. Then these are cross-section data. Here cross-section coordinate is failure station and elevation, downstream reach length, left over bank, the main channel, right over bank. Here Manning's value at left over bank, at the main channel, and at right over bank, and main channel bank station at the left and at the right. And this one is not that much used in the computation. So downstream reach length, there is no downstream station, so I have to say 0. Here also 0, 0. Then you can say apply data. The next one is to enter again the upper station before this station. So add new cross section. This is the river station again at upstream 15 kilometers from the downstream. So 15 is just a station name. So let's say OK. So here the downstream reach length is 15 kilometers. So 15,000 meters. Right over bank, and the main channel is also the same, and the right over bank is also the same. These data will be entered later on. Again, add new cross section at the upstream from this one. So let's say 30, the name of station, and this appears 15 kilometers upstream from the previous one. So 15 kilometers, 15 kilometers, 15 kilometers. Again, select add new cross section. Again, the next one, 5, represent 45 kilometers. Then the downstream reach length is the same one, 15,000, 15,000, 15,000. These numbers are here given in the problem. Each station is far apart from the previous by 15 kilometers. So, and the last upstream is 15 kilometers far away. So let's say add new cross section, and this one is at 16 kilometers. So let's say the name 16, and it is again 15 kilometers upstream, and the downstream station is far away, 15 kilometers. So apply data. Here we have station 60, 45, 30, 15, 00. Then again 60. Here At 00, we have no downstream reach station. These data are given in the problem, so I prepared the cross-section coordinates in Excel. This ones here, this is the chain edge, this is the elevation at each point, this is at 45, this is at 30, this is at 15, and this is at 00 station. So these bolded ones are the main channel, representing the main channel. Here also representing the main channel point. Beyond this is the right bank. Beyond this one, this is the left bank. Here again, this one is the left over bank, and after this point, this is the right over bank. So if I copy this one, Control C, then at 00 I can paste here the cross-section coordinates. So select or highlight some point and paste it. Control V. So these are the points, and here leftover bank station are bolded ones. So this one are here given 0 and 15, 64.8. So the last numbers. Here 0 and this one. Let's say apply data, it will show here. This red colored one is the main channel bank stations, and Manning's N value is the same over the main channel, right over bank, left over bank, and its value is given here as 0.0245. This is the same or constant for the whole river ridge, or 60-kilometer river ridge, represented by these Manning's. Actually, in real river, this is not the case, but for this example, we will use that number. So apply data here. The Manning's coefficient is represented as a whole main channel. Similarly, for 15, I will copy, I will write here in the same way. I will fill this data. After filling this data from the given data here, so it will look like this one. For station 30, it will look like this one. For 45, it will look like this one. Here, if you see, this is an error and this point is not that one, so we need to correct that one. Here for 45, or this one for 337 and 4817. So enter 4817, copy, Control V. So when you say apply data, shows the correct one, and this one is for station 60 for the last part, so for the most upper upstream point of the river or the ridge. Okay, after filling this one, this is all about the geometric data, and close this one, and here come here and save geometric data. Select geometric data and say geometric data for Unsteady flow. Say okay, here file name is in this one, this is the title. Okay, then close geometric data, and our problem is unsteady. This is because here the given peak flood is a triangular hierograph. So this triangular hierograph enters river ridge, and the peak reaches at time 10 hour and it ends at 20 hour. It is symmetric, and we will use this value, this peak one, and you can use the other two peaks for 500,000 years return period. So I will simulate by using 100 years peak flood of 20,000 metric cube per second. So for this, to enter this given data, here come edit, then select unsteady flow data. These are the types, and select boundary condition here, and this is the boundary condition parameters. And if you add other stations, here we have downstream most and upstream most station 60 and 00. So I need these stations and I don't need any other station. So to enter this flow hydrograph, I need upstream. So when I select this point, and this option is activated, so select flow hydrograph and use simulation time. So the simulation type I will use today's date, and when it starts at 00, so let's say 00, and the peak is after 10 hours, and its value is 20,000, and it ends because it is symmetric triangular, so it ends at 20 hours. So 20 0, and HecRAS fills this between numbers by interpolation. So select interpolate missing values. So the other values are filled. Then click OK. Flow hydrograph. And for the downstream ridge, select the boundary condition here, and I will use normal depths, and the friction slope is given the problem here. The friction slope assumed one is 1.43 times 10 to the power negative 5. So 0 0 0 0 1 4 3. Say okay. This one is for the downstream boundary condition, and the other given is initial condition flow, and this initial flow is through the whole reach, so not only for the upstream station, for the whole station. So I need to enter that stations and so add, then select all river station and click here, then all river stations are selected and say okay. So all stations are, and so this initial flow value in the river is 9,000 meter cube per second. So 9,000. Control V. I control. Now I am pasting. So paste. These are initial conditions. Then you can select apply data. Then finally save unsteady flow data. Let's say unsteady for river Y. Unsteady flow. River Y. Let's say okay. Then close unsteady flow data. The last step is to run HecRAS, and for that case select run, then our computation is unsteady, so select unsteady flow analysis, and here for plan give an ID, let's say 001, and it will process this one geometric file unsteady, and simulation time window, starting date, use today's date, ending date again today, starting time today at 00 and today at 20 hours, so 20 hours. Then say compute. HecRAS processing the result. If there is any error, it will show here. Okay, it processed unsteady flow simulation and close this one. can close this one, and the final one is to view the results. So select view, and you can select cross section here at the upstreammost water level, this one. And if you want to animate for the period 20 hours, so click here. This is animation. Here at 7, 8, 9 hours, the flow is changing. It's in 4:45. Again, you can animate this one. Here the peak reaches at somewhere here. If you want to see detail output table, this is the output: velocity head, water surface elevation, energy, slope, the total flow, here this is for cross section, and if you select flow distribution, it has another value. Or if you want to look XYZ profile, you can select here, rotate. So this is the main channel, and this is the bank stations, the left over bank, the right over bank stations. Or if you want to see the profile summary table, here at 20 hours, total flow at 60 at every station. And if you select standard table 2, again 20 hours, and if you select encroachment 1, how it encroaches to the banks, the left, the main channel, and there's no encroachment at 20 hours. Thanks for watching. This is all about today's tutorial. Please like, share, and write comments. Have a nice day.